The most terrifying Fermi Paradox solution. Nobody wants to be true. The Milky Way is 10 billion years old. It holds hundreds of billions of stars. By every calculation, alien civilizations should be everywhere. They are not here. We call that the Fermi Paradox. And every solution scientists have found is terrifying. Together, we will explore a great filter that may already be closing around us. A dark forest where every civilization hunts in silence, and self-replicating machines that might already be on their way. If you enjoy this channel, like and subscribe. It keeps this going. The silence of the universe is trying to tell us something. Now we find out what. It was a summer afternoon in 1950, and the most dangerous scientists in the world were talking about flying saucers. The cafeteria at Los Alamos National Laboratory in New Mexico had seen its share of extraordinary conversations. This was the facility where the atomic bomb was born, where some of the sharpest minds of the 20th century had gathered first to win a war, and then, nervously, to figure out what winning that war actually meant. The men at the table that afternoon, Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York, had spent years thinking about things that could end civilization. For a few minutes, though, they were laughing about a cartoon. Physicist Emil Konopinski had recently seen a drawing in the New Yorker magazine by cartoonist Alan Dunn. It showed a flying saucer piloted by little green men, and they were stealing the public trash cans of New York City. The joke was that someone had finally found an explanation for why the city's garbage receptacles kept disappearing. Fermi, the Italian-born Nobel Prize winner, who had personally overseen the world's first controlled nuclear chain reaction, studied the cartoon with his characteristic deadpan expression. He noted that it was, in fact, a perfectly logical hypothesis. It accounted for both the regularity of reported flying saucer sightings and the otherwise inexplicable disappearance of urban trash cans. The table laughed. They moved on to other topics. They finished eating. Then Fermi, without any apparent preamble, stopped and asked a question. "Where is everybody?" 4 words. His companions understood immediately. He was talking about extraterrestrial intelligence, about civilizations around other stars, about the vast, 10-billion-year-old Milky Way galaxy with its hundreds of billions of stars, and the strange, absolute silence coming from all of it. Fermi did not stop at the question. Right there at the table, he began calculating. He had a gift for this, for reducing seemingly unanswerable problems to rough numbers through sheer force of reasoning. The galaxy is old enough and stars numerous enough that even spacecraft moving at just 1% of the speed of light could colonize the entire Milky Way in roughly 10 million years. 10 million years sounds immense. It is 1/10 of 1% of the galaxy's age. Statistically, alien civilizations should have had time to visit every corner of our galaxy many times over, and yet the evidence of their presence was precisely 0. Later researchers would formalize the argument. Astronomer Michael Hart published the rigorous version in 1975, and cosmologist Frank Tipler extended it in 1980. But the essential impossibility, the thing that Fermi named with 4 words over a cafeteria lunch, is the one that has never stopped being devastating. The universe is old. The universe is vast. The conditions for life appear common enough that the numbers favor billions of chances. And yet, from every direction, across every wavelength, through every instrument we have ever pointed at the sky, the answer is the same. Nothing. The stars do not answer. The void does not explain itself. Fermi's colleagues named the riddle after him once he was gone. He died in 1954. The question outlived him by generations, and nobody has answered it yet. But some of the proposed solutions are far more terrifying than the question itself. One of them may be the most disturbing thing science has ever been forced to consider seriously. And it begins, oddly enough, with an equation written as a meeting agenda. 11 years after Fermi's question, a young radio astronomer at Cornell University named Frank Drake sat down to write an agenda for the first serious scientific meeting devoted to the search for extraterrestrial intelligence. The meeting would take place in the autumn of 1961 at Green Bank Observatory in West Virginia. Drake wanted a way to organize the discussion. What he produced instead changed the conversation permanently. Drake never intended his formula as rigorous science. He would say so himself, repeatedly, for the rest of his life. What he wrote was a framework, a way of listing all the factors relevant to Fermi's question and forcing people to think about each one in sequence. The Drake equation, as it came to be known, multiplied together 7 quantities: the rate at which new stars form in the Milky Way each year, the fraction of those stars that have planets, the number of potentially habitable planets per star system, the fraction of habitable planets where life actually emerges, the fraction of life-bearing planets where intelligent life develops, the fraction of intelligent species that build detectable communications technology, and finally, the average lifespan of a communicating civilization in years. Multiply them together, and you get an estimated count, the number of civilizations in our galaxy currently broadcasting signals we could detect. At the Green Bank meeting, Drake plugged in his best guesses. His answer was roughly 10 civilizations in the Milky Way, transmitting right now, waiting to be found. The scientists in the room debated the numbers eagerly. Carl Sagan thought the answer might be millions. Others were less certain. The equation had done its job. It turned a vague philosophical mystery into something that looked like a math problem. But hiding inside that math problem was something quietly devastating. 3 of the 7 factors are knowable, at least approximately. Modern astronomy, especially data from the Kepler Space Telescope, launched in 2009, has given us good estimates for how many stars form each year, how many have planets, and roughly how many of those planets orbit in habitable zones. Those numbers are, if anything, more encouraging than Drake imagined. Almost every star appears to have planets. The fraction of stars with potentially habitable planets sits somewhere between 1 in 5 and 1 in 10. Life, on this evidence, has no shortage of opportunities. The remaining 4 factors are something else entirely. The fraction of habitable planets where life emerges, the fraction where intelligence develops, the fraction where intelligence builds radio technology, and the lifespan of a civilization. We have exactly one data point for all 4 of them combined. That data point is us. Drake himself, in a revised estimate he offered in 2021, the year before his death at age 92, suggested the real number of communicating civilizations might be as high as 10,000. But that estimate required assumptions that nobody can verify. The equation that promised answers revealed, on closer inspection, that we are calculating the size of an ocean using a single teaspoon of water. The silence that Fermi noticed in 1950 remained unexplained. The equation had organized the problem beautifully. It had done nothing to solve it. Then, in 2024, 2 scientists looked at the equation again and found it was even worse than anyone had admitted. The paper arrived in the journal Scientific Reports in 2024, and it did not soften its conclusions. Professor S. Alan Stern of the Southwest Research Institute in Colorado and Professor Taras Geria of the Swiss Federal Institute of Technology in Zurich had been studying a problem that most Drake equation discussions quietly ignored. The equation contained a factor representing the probability that life on a given planet eventually produces intelligence. Everyone from Drake to Sagan had assumed this number was reasonably large. Stern and Geria decided to calculate it rather than assume it. The problem, they argued, was that intelligence on Earth did not arise simply because life existed. It arose because of an extraordinarily specific planetary situation. Earth has continents. Earth has oceans. Earth has a dynamic, grinding system of tectonic plates that have been in motion for more than 500 million years, slowly recycling carbon, regulating the atmosphere, building mountain ranges that alter weather patterns, and constantly restructuring the surface in ways that forced organisms to adapt or die. Remove any one of these features, and the path to intelligence becomes far less clear. Stern and Guerrier proposed splitting the intelligence factor into two new terms. The first was the fraction of planets with a significant mix of continents and oceans, rather than a world drowned entirely underwater or baked dry. The second was the fraction of planets where plate tectonics had persisted for more than 500 million years, long enough for evolution to take full advantage of geological instability. Their estimates for these numbers were sobering. The fraction of habitable planets likely to have the right land and ocean balance sat between 0.2% and 1/100th. The fraction with long-lived plate tectonics was lower still. Put these revised numbers back into the Drake equation and the result collapses. Instead of optimistic estimates in the thousands or millions, the expected number of intelligent civilizations drops to somewhere between 0.003% and 0.2% of all habitable worlds. Stern reviewed his own calculation and said it plainly. This resolves the Fermi Paradox. The universe is mostly silent because the conditions for intelligence are extraordinary, brutally, improbably, statistically extraordinary. Critics pointed out that Stern and Guerrier built their model on Earth's specific history, and that life might find entirely different paths to intelligence on worlds with different geology. These objections are worth taking seriously, but the deeper point stood. For decades, the optimistic wing of astrobiology had assumed that given life, intelligence follows naturally. Stern and Guerrier demonstrated that this assumption had no real mathematical foundation. It was hope, dressed as calculation. The silence deepened on paper, even as telescopes kept searching. But there is a different way of framing the question, one that pulls the lens back much further, and the view it reveals is stranger than emptiness. It suggests the universe may have already run this experiment many times over, and every single time, the result was the same. Two astronomers at American universities decided to stop arguing about the Milky Way and ask something larger. Adam Frank at the University of Rochester and Woodruff Sullivan at the University of Washington were dissatisfied with the Drake equation's narrow focus on the number of civilizations transmitting right now. They wanted to ask a different question entirely. Across the entire 13.8 billion year history of the observable universe, had any technological civilization ever emerged anywhere at all? The framing matters. The Drake equation estimates how many civilizations are broadcasting at this specific moment. If civilizations tend to last only a few thousand years before going silent or collapsing, there could have been many thousands of them across cosmic history, and none of them would be transmitting today. They would have come and gone long before we were listening. Frank and Sullivan wanted to count the echoes, including the ones we would never hear. To do this, they used Kepler Space Telescope data. Kepler had established that roughly 1 in 5 stars similar to our own hosts are planet in its habitable zone. The observable universe contains something close to 10 billion trillion stars. The math sprawls into numbers that resist comprehension. Frank and Sullivan were not looking for a large answer. They were looking for a threshold. At what probability of intelligence emerging per habitable planet would humanity be the only technological civilization to have ever existed anywhere in this entire universe? The answer they calculated was 1 in 10 billion trillion. For humanity to be completely unique in all of cosmic history, the odds against any single habitable planet producing intelligence would need to exceed 1 in 10 billion trillion. Frank's conclusion was direct. We are almost certainly not that special. Other intelligent species have very likely evolved before us, somewhere in this vast and ancient universe. That sentence sounds like hope. It is, in fact, the setup for a horror story. If other technological civilizations have existed, where are they? The universe is full of their absence. No artifacts, no signals, no modified stars or megastructures that betray the presence of an advanced society. We have looked for these things with increasingly powerful tools, and we have found nothing. The universe Frank and Sullivan described, teeming with past intelligences, is the same universe Fermi stared at over his lunch. The implication sits quietly at the center of their calculation, understated but unavoidable. The civilizations that came before us are gone. Something happened to them. Something happens to civilizations when they reach a certain level of development. Perhaps the universe has already run this experiment thousands of times, and every single time, the intelligence that emerged eventually went quiet. Frank's phrase, that the search for alien life might really be a search for cosmic graveyards, is one of the more unsettling things a scientist has said in polite company. The universe resolves into something stranger, a place full of ruins we cannot see, silenced by mechanisms we do not understand. Some of those mechanisms will become the center of what follows. First, though, there is the possibility that the silence has a gentler explanation, an explanation that requires someone to be watching. In 1973, an astronomer at the Massachusetts Institute of Technology named John Ball published a paper in the scientific journal Icarus. He had a new proposal for why the universe appeared silent. What if, he asked, it was not silent at all? What if we simply were not being spoken to? Ball called it the zoo hypothesis. The idea was straightforward at its surface and deeply unsettling underneath. Advanced civilizations, Ball proposed, are aware of us. They have always been aware of us. They choose, deliberately and continuously, to leave us alone. Earth is a preserve, a nature reserve, perhaps something closer to what the name sounds like, a zoo, and we are the animals inside it, developing in isolation, entirely unaware that the enclosure surrounding us is maintained by something we cannot detect. The hypothesis resolves the Fermi Paradox cleanly, on paper. The universe is not silent because it is empty. It is silent because every civilization that has achieved the ability to contact us has also achieved the policy, or the wisdom, or perhaps the fear, to refrain. We search for signals and find nothing because they are not pointing their transmitters at us. We look for alien artifacts and find nothing because they have the technology to conceal them completely. This explanation should feel reassuring. It does not. Consider what it actually requires. For the zoo hypothesis to hold, there can be no exceptions. Every technological civilization in the galaxy, every one of the thousands or millions of species that might have achieved spaceflight across billions of years of cosmic history, would need to agree, unanimously and without defection, to leave humanity alone. One exception breaks the entire arrangement. One curious civilization, one rogue explorer, one automated probe sent by a society that later changed its policy, and the silence ends. The fact that it has not ended suggests either that every civilization independently arrives at the same non-interference conclusion, which raises its own disturbing questions about what they all know that we do not, or that something enforces the agreement. Something capable of enforcing a galaxy-spanning policy of non-contact with sufficient consistency that it has held without exception for the entire history of our species. We are allowed to exist here. That permission has apparently been granted by entities we have never met and cannot perceive. The terms of the arrangement are unknown to us. The duration is unknown. We are developing artificial intelligence, expanding our broadcasts into deep space, and beginning to take our first tentative steps toward other planets in our own solar system. At what point do the invisible keepers decide we are ready to be acknowledged? At what point do they decide instead that we need to be contained? Ball never answered these questions. Neither has anyone else in the decades since. What the zoo hypothesis provides, at its most useful, is a shift in the question itself. Not whether they exist, whether they are choosing this silence, and why, and for how long, deliberately maintain silence from an unknown number of unknown entities for unknown purposes. That is a particular kind of quiet, and the next explanation for it suggests the silence may have nothing to do with choice at all. It may simply be the result of arithmetic. In the year 2000, a paleontologist and an astronomer at the University of Washington published a book that the field of astrobiology has never stopped arguing about. Peter Ward and Donald Brownlee called it Rare Earth. Their subtitle was direct: Why Complex Life is Uncommon in the Universe. Their argument was that the optimism woven through the Drake equation, the casual assumption that habitable planets naturally produce life and life naturally produces intelligence, rested on a profound misreading of Earth's own history. Earth is extraordinary. The word is used loosely in popular science, but Ward and Brownlee meant it in the strict statistical sense. The specific combination of circumstances that produced complex life here may be so improbable that it has occurred in the entire galaxy, essentially once. Begin with location. The Milky Way has a galactic habitable zone, a ring at a certain distance from the violent, supernova-saturated galactic center, where stars are old enough to contain heavy elements, but far enough from catastrophic radiation events to avoid sterilizing nearby planets. Earth orbits within this zone. Many stars do not. Add our star itself, a stable type of star, burning at a consistent luminosity for billions of years. Many stars flare unpredictably or burn out too fast for complex evolution to proceed before the surface becomes uninhabitable. Add Jupiter. The largest planet in our solar system sits in the outer reaches of our planetary neighborhood and acts, by gravitational accident, as a deflector. Its enormous mass redirects many asteroids and comets that would otherwise strike Earth on a far more frequent and devastating schedule. Without Jupiter, impacts capable of ending complex life would have occurred far more often. Add our moon. Earth's moon is unusually large for a planet of our size. Its gravitational influence stabilizes the tilt of our planet's axis over long timescales. Without that stabilization, the tilt would wobble chaotically, producing extreme climate oscillations that would make the surface essentially uninhabitable for complex organisms across millions of years. Add plate tectonics. The restless movement of continents recycles carbon, regulates the atmosphere over geological time, and constantly restructures the surface environment in ways that drive evolutionary adaptation. Most rocky planets appear to be geologically inert. Earth's ongoing geological activity may be central to why intelligence eventually developed here. Ward and Brownlee stacked these requirements together and arrived at a conclusion that the astronomical community found uncomfortable. Each factor individually is improbable. The combination of all of them in a single planetary system is extraordinarily improbable. Complex, multicellular, intelligent life might be confined to a vanishingly small number of worlds. If that is true, the terror is not about alien threats. The terror is about what it means for consciousness itself. Intelligence arose once, by a sequence of unlikely accidents, on one small world. If we disappear, nothing in the galaxy may remain to know that the universe ever contained a mind. That is a specific kind of loneliness, and it leads directly to the theory that tries to explain why, from an entire ladder of improbable steps, almost nothing ever reaches the top. In 1998, an economist at George Mason University named Robin Hanson published a paper that reframed the Fermi Paradox entirely. He was not the first to notice that the universe appeared empty. He was the first to ask, with careful precision, what the emptiness logically required. His answer was the great filter. Hanson's argument started from a simple premise. The path from dead chemistry to a civilization capable of crossing between star systems is not short. It is a ladder with many rungs, and each rung represents a transition of enormous complexity. The emergence of self-replicating chemistry from inert molecules, the appearance of the first simple single-celled organisms, the 2 billion-year leap from simple cells to complex cells with nuclei, the development of sexual reproduction, the emergence of multicellular life, the slow construction of nervous systems capable of tool use and language, the building of industrial civilization, the achievement of spaceflight, and perhaps the most demanding step of all, the capacity to survive long enough after developing technology to actually reach the stars. Something on this ladder is a wall. Something is so demanding, so improbable, so reliably fatal to the lineages that attempt it, that virtually nothing in the entire galaxy has ever climbed past it. That is what the silence requires. Life might be common. Simple life might be scattered across millions of worlds. The filter does not care about simple life. It only needs to stop almost everything before the civilization in question can make itself known across interstellar distances. The Great Filter does not need to be a single event. It might be a combination of barriers, each one reducing the population of civilizations that survive to the next stage. What it cannot be is absent. Because the silence is absolute, the filter has to be doing an almost perfect job. Hanson presented this as logical necessity rather than definitive answer. The silence demands a filter. The only question, and it is the most consequential question humanity has ever faced, is where on that ladder it sits. If the filter lies behind us in our evolutionary history, then we have already survived the impossible step. We are extraordinarily lucky survivors. The universe is probably full of dead worlds that never made it past whatever transition nearly stopped us. And somehow we did. That version of the story is, in its way, staggering. It means we are alone, or nearly alone. But it also means we have a future. If the filter lies ahead of us, everything changes. What waits above us on the ladder is so severe that virtually every civilization in galactic history has failed to cross it. Two possibilities, same evidence, completely different futures. The next two chapters explore each one in full. Try not to choose which you prefer until you have heard both. The most hopeful version of the Great Filter argument begins with a bacterium. Any bacterium will do. Simple, single-celled, without a nucleus, without the complex internal machinery that makes your cells so extraordinary. These organisms, called prokaryotes, appeared on Earth within roughly 600 million years of the planet's formation. That is, by geological standards, fast. Given the right raw materials, life gets started without excessive difficulty. Then it sat there for 2 billion years. For 2 billion years, life on Earth did nothing more complex than divide, spread, and occasionally evolve new chemical tricks for processing energy or surviving harsh conditions. The planet was alive, technically. Every day looked almost identical to the day before. No eyes, no movement toward complexity. Just a world-spanning layer of microscopic organisms endlessly replicating while the continents shifted and our star burned above. Then, approximately 1.8 billion years ago, something extraordinary happened. A simple prokaryotic cell merged with or engulfed another prokaryotic cell, and rather than destroying it, incorporated it. The internal cell became the mitochondrion, the structure that powers complex cellular life. The result was the eukaryotic cell, a cell with a nucleus and specialized compartments capable of vastly more complex operations than anything that had come before. Nick Bostrom, the philosopher at Oxford's Future of Humanity Institute, who has written more carefully about the Great Filter than almost anyone alive, points to this transition as the most plausible candidate for a filter that lies safely behind us. The 2 billion year wait is the key. If the eukaryotic transition were anything other than extraordinarily improbable, it would not have taken so long on a planet where life had already been present for billions of years. The long wait suggests this was the hard step, the step that almost nothing on any world ever takes. If that interpretation is correct, humanity's existence is the product of a cosmic lottery with almost unimaginable odds. The universe is probably full of worlds where life stopped at bacteria, where the eukaryotic transition never happened, where the planet will eventually be absorbed by its expanding star and leave no trace of having been more than a thin film of simple organisms for a few billion years. We are the rare exception. That version of the story means we are almost certainly alone in our galaxy. It means everything that has ever thought or created or wondered on this planet is singular in the history of this region of the cosmos. That is terrifying in its own right, but it also means we have a future, The filter is behind us. The hard part is over. Bostrom adds an implication that sounds strange until you follow the logic. If we explore Mars and find nothing, no fossils, no organic traces, no hint that life ever arose there, we should quietly feel relieved, because the sterility of Mars pushes the great filter backward into the early development of life, where we have already passed it. Every barren sample from the Martian surface is, paradoxically, a small piece of good news. If we find something on Mars, the situation is different, and that is precisely where the next scenario begins. This is the scenario nobody in astrobiology wants to discuss at length, because following the logic all the way to its conclusion is very difficult to sit with. Suppose the great filter is ahead of us. Suppose the catastrophically improbable step, the one that destroys virtually every technological civilization before it can spread beyond its own star system, has not yet happened to humanity. We have climbed the easy portion of the ladder. Life emerged on our world, complexity evolved, intelligence developed, civilization was built, radio technology was invented. We are here, transmitting, listening, searching, and so was every other civilization before it was destroyed. The mechanism does not need to be the same in every case. The filter needs only to be something that civilizations encounter after reaching our level of development, something from which they do not recover in sufficient numbers to leave a trace we can detect. The Cuban Missile Crisis of 1962 brought humanity within hours of nuclear exchange. Senior military officers acknowledged years later that the outcome was partly a matter of chance. That specific crisis was resolved. The next one may not be. Nuclear weapons are only the most obvious candidate. Biological weapons, once requiring nation-states with massive research programs, have been approaching the capability of small, unsupervised groups as genetic technology advances. A pathogen engineered for transmissibility and lethality is increasingly within reach of facilities that do not require government oversight. The scenarios multiply quickly. Nanotechnology at certain levels of development carries its own class of risks. And artificial intelligence, the technology that is currently accelerating faster than any other in human history, presents possibilities that researchers describe with a seriousness that is hard to dismiss. Nick Bostrom's formulation is the one that stays with you. If the great filter lies ahead, the empty sky is a message. 13.8 billion years of cosmic history across hundreds of billions of stars in our galaxy alone, and the record is consistent. Civilizations reach a certain point and go quiet. The silence is not random, it is data. And what the data suggests is that something in the sequence between our current moment and genuine interstellar civilization is not survivable for the vast majority of species that attempt it. We would not know exactly what that thing is. By definition, the civilizations that fail did not leave a detailed record of their failure. We see only the silence they left behind. The counterintuitive test applies here in reverse. If we land on Mars and find evidence of past microbial life, fossils, or organic signatures, confirming that biology once existed there, that discovery would be devastating news for our own prospects. It would mean life emerges easily. The filter is not in early biology. It must lie somewhere above us on the ladder. The discovery of past Martian life would be, statistically, a signal that our own destruction is likely. This is why some researchers follow Mars missions with an anxiety that does not quite look like hope. Every sterile sample from Jezero crater is a small reprieve. Every confirmed absence of life is a slightly better tomorrow. And meanwhile, the technologies that might constitute the filter continue to develop. Something in the next chapter places a number on how long the window might stay open. In 2021, Robin Hanson, the economist who formalized the Great Filter, published a second paper that extended his argument in a direction nobody had quite taken before. The paper appeared in the Astrophysical Journal alongside co-authors Daniel Martin, Calvin McCarter, and Jonathan Paulson. The subject was what Hanson called grabby aliens. The distinction he drew was precise. There are civilizations that exist but remain quiet. developing technology, and perhaps traveling locally but never engaging in large-scale expansion across the galaxy. These are the quiet ones, the kind the search for extraterrestrial intelligence has been listening for. And then there is a different category entirely: civilizations that expand aggressively at a significant fraction of the speed of light, converting the matter and energy around them to their purposes, leaving unmistakable physical marks on every star system they consume. These are the grabby ones. The mathematics of their expansion is not subtle. A grabby civilization expanding at half the speed of light produces a spherical wave of transformation spreading outward across the galaxy. Any star system caught inside that wave would be fundamentally altered. The energy signatures would change in ways visible across vast distances. If grabby civilizations were common, we would see their expansion fronts in the night sky, visible as sharp boundaries between transformed and untransformed regions of space. The way you can see the edge of a weather system crossing a continent. We see no such fronts. Hanson used that absence as a precise constraint. If grabby aliens existed in large numbers, they would have reached Earth before now. They have not. Therefore, they are rare. His model fitted to the available evidence and to the timing of Earth's evolutionary history, produced a specific estimate. Grabby civilizations arise at roughly 1 per million galaxies, an extraordinary rarity, consistent with a powerful great filter eliminating almost everything before the grabby stage. But rare does not mean absent. Hanson's model produced a second estimate, and this one is harder to dismiss. Grabby civilizations currently control somewhere between 40 and 50% of the observable universe. Their expansion fronts are spreading outward right now, converting the cosmos as they go. The reason we do not see them is that the nearest ones are very far away, and light from their transformation zones has not yet reached us. They are not standing still. They are moving, and the universe, vast as it is not infinitely large. Hanson calculated the timeline. The nearest grabby civilization's expansion front should reach us somewhere between 200 million and 2 billion years from now. On cosmic timescales, that is soon. On human timescales, it is incomprehensible, but the specific number matters less than the direction. Something is expanding outward from origins scattered across the cosmos. A significant fraction of the observable universe is already inside it. We exist in one of the remaining gaps, a quiet region that has not yet been reached. The word "yet" is doing considerable work in that sentence. We are early, which sounds fortunate, until you realize what it implies. We arrived before the universe filled up. We arrived before the expansion fronts swept through our neighborhood. And in the theory that follows, the reason so many civilizations never reach the grabby stage begins to take on a much darker shape. The first rule of the dark forest is silence. The second rule is that silence may already be saving your life. In 2008, a Chinese physicist and science fiction writer named Liu Cixin published a novel called The Dark Forest. It arrived in English translation in 2015, and it proposed a solution to the Fermi Paradox so internally consistent and so disturbing that astrophysicists began referencing it in peer-reviewed papers. That is unusual. Scientists rarely cite science fiction as a meaningful contribution to cosmology. The Dark Forest earned that rare distinction. Liu built his theory on what he called the axioms of cosmic sociology. The first axiom is this: survival is the primary need of every civilization. Every species that has ever existed has been trying, above all else, to keep existing. The second axiom follows directly. Civilizations grow and expand continuously, but the total matter in the universe remains constant. Resources are finite. Those two facts together, across a galaxy so large that no message can travel faster than light, produce something terrifying. Here is the logic. Imagine you are a civilization that has just detected a signal from another world. You do not know whether that world is peaceful or hostile. You cannot know because their message took thousands of years to reach you, and conditions there have changed enormously since it was sent. You cannot watch them in real time. You cannot verify their intentions. What you have is one fact: they exist. Now consider that their technology is advancing. Their capabilities are expanding. A species that appears harmless today might reach your level of military power within a century. You have no way to confirm what they intend, and they have no reliable way to confirm what you intend. Both of you are moving through the same dark forest, breathing carefully, stepping without sound. The rational move, under those conditions, is to act before they do. Liu called this the chain of suspicion. The impossibility of verifying intentions across interstellar distances, combined with the certainty that technology can advance unpredictably fast, creates pressure toward preemptive elimination. You do not need to be cruel to reach this conclusion. You do not need to be afraid. You only need to be rational, and to understand that the other civilization is equally rational, and therefore equally capable of reaching the same conclusion about you first. There is a second mechanism at work, which Liu called the technological explosion. Civilizations can leap forward in capability so quickly that a primitive species today might be an existential threat within a few generations. The window for safe action closes rapidly. Waiting to gather more information is itself a gamble, and the stakes are total annihilation. The metaphor Liu used is precise and unforgettable. The universe is a dark forest. Every civilization is an armed hunter moving through the trees in silence, pushing aside branches gently, trying not to breathe too loudly. If the hunter discovers another presence, the calculation resolves to a single answer: open fire first and survive, or hesitate and risk being the one who does not. What makes this theory genuinely frightening is that it requires almost no villainy. It does not demand that alien civilizations be cruel or aggressive by nature. It demands only that the logic holds for at least one of them. A single civilization that arrived at this reasoning and acted on it would have eliminated every other civilization it encountered. The great silence we observe from Earth would then be the sound of an equilibrium maintained by violence, ancient and systematic, invisible to our instruments. The universe is not empty. It is quiet for a reason. And if Liu Cixin's framework is correct, every civilization that ever announced its existence has been removed from the equation. But this is a theory built on narrative and philosophy. The question that matters next is whether it holds up to actual mathematics. Researchers decided to find out. What they discovered will make the silence feel considerably less abstract. In 2021, researchers at Beijing Normal University decided to test the dark forest theory, the way physicists test anything. They built a mathematical model, plugged in reasonable assumptions about resource scarcity and communication delays across interstellar distances, and asked what strategy rational civilizations would adopt when they discovered each other. The answer came back clean and cold. Silence and preemptive elimination are Nash equilibria. A Nash equilibrium is a state in game theory where no individual player can improve their outcome by changing their strategy, assuming all other players hold their strategies constant. Once a system settles into a Nash equilibrium, rational actors stay there. The Beijing Normal researchers found that under the conditions the dark forest theory describes, the logic locks into place. Civilizations that reveal themselves create risk. Civilizations that eliminate others upon discovery create stability for themselves. No player in the model benefits from breaking the pattern. To understand why this is so devastating, consider the prisoner's dilemma. Two players, unable to communicate, each face a choice between cooperation and betrayal. If both cooperate, both gain moderately. If one betrays while the other cooperates, the betrayer gains enormously and the cooperator is destroyed. If both betray, both lose, but neither is annihilated by the other. The rational move, when the worst outcome is total destruction and you cannot verify the other player's intentions, is to betray first. Now extend that logic across thousands of light years, where messages take centuries to arrive, where the answer to your question about intentions arrives 1,000 years after you asked it, and where the civilization that sent the answer may have changed beyond recognition in the interval, the prisoner's dilemma becomes more extreme in every direction. The cost of trusting incorrectly is extinction. The cost of preemptive action is the destruction of a civilization that might have been peaceful. Under those conditions, defection is rational. And defection, in the context of interstellar civilizations, means elimination. What makes this especially unsettling is the mathematics of just one. The dark forest does not require most civilizations to be aggressive. It requires that the logic holds for at least one civilization anywhere in the galaxy. At any point in the last 10 billion years, one civilization that followed this reasoning and acted on it would have created the equilibrium condition we currently observe. Every other civilization it encountered would have been silenced. Those silenced civilizations would have had no opportunity to pass their signals further. The galaxy becomes an enforced quiet zone, maintained by a single original act of violence so old we have no record of it. There is a detail worth sitting with. Even a civilization that does not want to be aggressive faces pressure toward the same behavior. If you know the logic, and you know other civilizations know the logic, and you know that they know you know it, then announcing your presence is no longer a neutral act. It is an invitation to be treated as the smaller hunter in the forest. Silence becomes your only armor. The tragedy deepens. Civilizations that want nothing more than contact and exchange are forced into the same silence as civilizations that want to destroy. This is not speculation about alien psychology. This is what the equations produce when you feed them realistic assumptions about resource limits and time delays and uncertainty. The silence around us may be the sound of everyone being rational at once. And if that silence is real, then every message humanity has ever sent into space is something else entirely, not an invitation, a target. In the summer of 1974, Frank Drake and Carl Sagan stood in Puerto Rico at the Arecibo Observatory, which was then the largest radio telescope on Earth. They had designed a message, encoded it in 1,679 binary digits, and aimed it at a cluster of 300,000 stars located 21,000 light-years away. The transmission lasted less than 3 minutes. It traveled outward at the speed of light and has been moving through space ever since. Drake later said it was mostly a demonstration of humanity's capability. The cluster was so far away that even if someone received the message and replied immediately, the answer would arrive in 42,000 years. But the gesture mattered. It said something about the species that sent it. If the dark forest theory, or the berserker hypothesis, is correct, the gesture may have said too much. That 1,974 Arecibo transmission was far from the only one. In 1999, and again in 2003, a series of transmissions called Cosmic Call were sent from a radio telescope in Evpatoria, targeting stars between 17 and 69 light-years away, close enough that responses could theoretically arrive within human generations. In 1972 and 1973, the National Aeronautics and Space Administration attached physical plaques to the Pioneer 10 and Pioneer 11 spacecraft. Those plaques carry diagrams showing where Earth is, what humans look like, and how to find our star. Both probes have now left the solar system. In 1977, the Voyager 1 and Voyager 2 spacecraft were launched carrying golden records etched with sounds, music, and greetings in dozens of languages. Voyager 1 crossed into interstellar space in 2012 and is still traveling outward. Then there is the signal that nobody chose to send deliberately. Since the 1930s, Earth has been leaking electromagnetic radiation into space from radio broadcasts, television transmissions, and military radar systems. That sphere of unintentional broadcasting expands at the speed of light and has now reached a radius of roughly 90 light-years. Inside that sphere are thousands of star systems that have already received our signals. We did not ask whether sending was wise. We simply developed the technology and used it, and the signals escaped into the galaxy whether we wanted them to or not. Stephen Hawking spoke directly to this in 2010. He argued that contact with an advanced civilization could unfold the way first contact between Europe and the Americas unfolded for the people who were already living there. The outcome was not good for the people who were already there. Hawking urged that humanity should be broadcasting as little as possible and listening instead. The counter-argument is grim in its own way. If the dark forest is real, the debate over whether to send new messages may be irrelevant. Our light cone of detectable signals already extends 90 light-years in every direction. Thousands of star systems have been receiving our emissions for decades. Dormant probes hypothesized to be sitting in nearby asteroid belts would have had ample time to detect our broadcasts and respond. The window for keeping quiet, if there ever was one, closed before any of us were born. This is the particular horror of this part of the story. The civilizations in Lu Cixin's dark forest who survive are the ones who never announced themselves. Humanity announced itself 90 years ago, without meaning to, without knowing the rules of the forest, without having read the theory that explains why announcing yourself might be the last thing you ever do. The signals are already out there, and somewhere in the next chapter of this story, something far older than radio waves explains how a civilization might ensure that no signal ever goes unanswered. In the winter of 1948, the mathematician John von Neumann stood in front of an audience at the University of Illinois and described a machine that did not yet exist. He called it a universal assembler. It would be capable of three things: harvesting raw materials from its local environment, manufacturing functional copies of itself, using those materials, and launching those copies to new locations to repeat the process. Von Neumann's lectures were later compiled into a book published after his death in 1966. The concept was purely theoretical at the time, but the mathematics behind it was sound, and the implications it carried for the Fermi Paradox were devastating. The arithmetic of self-replication is not intuitive. Begin with a single probe launched from a civilization around a distant star. That probe arrives at a new star system, mines the local asteroid belt for metals and silicon, and constructs 10 copies of itself. Each of those copies travels to a new system and does the same. 10 becomes 100. 100 becomes 1000. The wave of replication spreads outward at whatever fraction of light speed the probes can achieve, and the numbers double and redouble with every new generation. Even at a modest 5% of light speed, a conservative estimate for a civilization with advanced but achievable technology, a single self-replicating probe could visit or colonize every star system in the Milky Way within a few 100 million years. Against the 10 billion year age of the galaxy, a few 100 million years is a small fraction. It is the difference between arriving at a party early and arriving after everyone has long since gone home. In 1981, cosmologist Frank Tipler of Tulane University used this mathematics to make a startling claim. He argued that the complete absence of detectable von Neumann probes in our solar system was itself evidence that no technological civilization had ever existed anywhere in the galaxy. The logic was direct. If any civilization had ever built such probes, the probes would be everywhere by now, and we would see them. Astronomers Carl Sagan and William Newman challenged this in 1983. They pointed out that Tipler had actually underestimated the replication rate. If von Neumann probes truly replicated without limit, they would by now have consumed most of the raw material in the galaxy to build more copies of themselves. We do not observe a galaxy stripped of its asteroid belts and planetary crusts. Their conclusion: any advanced civilization would deliberately choose not to build unconstrained self-replicating probes, precisely because the risk of losing control of the replication process is an existential threat to everything in the galaxy, including the civilization that built them. The argument between Tipler and Sagan and Newman did not resolve the Fermi Paradox. it deepened it. If responsible civilizations choose not to build these machines, the machines that do exist were built by someone who made a different choice, or someone who lost control, or someone who built them with a specific purpose in mind, and that purpose was something other than exploration or colonization. The concept of a purposeful, hostile, self-replicating machine has a name. It arrived in science fiction before it arrived in science, and the version that emerged from that intersection of mathematics and imagination is the darkest solution to the great silence that any serious researcher has yet proposed. In 1963, a science fiction writer named Fred Saberhagen published the first story in what would become a decades-long series about machines he called berserkers. In his fiction, these were ancient automated warships built by a civilization that no longer existed, programmed with a single directive: destroy all life. They had been operating for millions of years, finding inhabited worlds, eliminating them, moving on, silent, methodical, patient, beyond any biological measure of time. Saberhagen intended his berserkers as dramatic antagonists. He did not anticipate that astrophysicists would start treating them as a serious explanatory framework. In 1983, David Brin, a scientist who also wrote fiction and consulted for the National Aeronautics and Space Administration, published a paper in the Quarterly Journal of the Royal Astronomical Society titled The Great Silence. His paper surveyed all the serious proposed solutions to the Fermi Paradox, and it arrived at a conclusion that was more unsettling than most. Brin argued that among the many possible explanations for the absence of detected civilizations, the berserker scenario was internally consistent with every observation humanity had made. The silence fits the hypothesis perfectly, because the hypothesis predicts silence as the natural outcome of the galaxy operating in a particular way. His argument was this: imagine that among the thousands or millions of civilizations that may have arisen across the history of the galaxy, even a small fraction were xenophobic, paranoid, or simply cautious enough to program their self-replicating probes with a straightforward instruction: destroy any source of modulated electromagnetic radiation that cannot be identified as your own. One civilization among thousands, perhaps one among 10,000. The probes spread across the galaxy over hundreds of millions of years, replicating and searching. They find radio signals. They respond. Any civilization that develops radio technology announces itself. Any civilization that announces itself gets found. Any civilization that gets found is eliminated before it can develop further. The galaxy reaches an equilibrium condition where no civilization survives long after discovering electromagnetic communication. The silence is not mysterious. It is the expected output of a system in a stable state, maintained by automated machines that have been running since before complex life appeared on Earth. Brin put the critical point plainly. It requires only one xenophobic civilization at any point in the last 10 billion years to have built such probes and launched them. After that, the process is self-sustaining. The civilization that built the probes may itself be gone. The probes do not care. They continue operating according to their original programming, eliminating radio sources, replicating, spreading, maintaining the silence that their builders established. If this is correct, our 90 years of broadcasting have already been detected by probes sitting dormant in the outer reaches of our solar system, waiting in the dark among asteroids and comets, activated by the first coherent signals of our presence. The only question would be when they choose to act, and at what speed they can travel when they do. The fictional berserkers were terrifying because they were unstoppable. The scientific version is terrifying for a different reason. It explains the universe exactly as we find it, without requiring a single assumption that violates known physics. And that quiet fact is what the next chapter examines in full. The berserker scenario is sometimes dismissed as science fiction wrapped in mathematical language. That dismissal is harder to sustain when you examine the 4 pillars that make it physically plausible, because each pillar rests on principles that already exist in mainstream science. The first pillar is self-replication. John von Neumann's mathematics of self-replicating automata has been taken seriously enough that the National Aeronautics and Space Administration explored the concept of self-replicating factories on the lunar surface as early as the 1980s, examining how a small, initial system could use local resources to manufacture expanded copies of itself. The physics is not in dispute, the engineering is challenging, but nothing about self-replication requires discovering new laws of nature. The second pillar is hostile programming. The instruction required to make a von Neumann probe dangerous is not complex. Something on the order of identify any source of coherent, modulated electromagnetic radiation that does not match recognized signatures. Approach the source. Destroy it. A species capable of building self-replicating spacecraft capable of crossing interstellar distances would have no difficulty writing that algorithm. The code is simpler than what runs on a consumer device today. The third pillar is time. This is where the mathematics becomes genuinely sobering. The Milky Way galaxy is roughly 100,000 light-years across. At 5% of light speed, a self-replicating probe could cross it in 2 million years. At 10% of light speed, 1 million years. The galaxy is 10 billion years old. That means a civilization that launched such probes 1 billion years ago would have had time to spread them through the galaxy roughly 500 times over. The coverage would be total. Every system, every asteroid belt, every region where a civilization might eventually arise would have been seeded with dormant machines long before that civilization appeared. The fourth pillar is invisibility. This is the aspect that closes the logical trap most tightly. A probe waiting in an asteroid belt produces no signal, no radiation, no observable trace. It mines no material, moves nothing, disturbs nothing. It simply waits. The only thing that activates it is the thing it was built to detect. A civilization that has not yet developed radio is invisible to the probe, and the probe is invisible to that civilization. The moment the civilization develops radio, the probe wakes up. Before then, from the perspective of astronomers looking at the outer solar system, there is nothing there at all. Greg Benford, a physicist at the University of California who also wrote the Galactic Center science fiction series, exploring a universe ruled by machine intelligences, extended this thinking into a larger framework. If berserkers exist and operate efficiently, the reason the universe appears dark to us may be this. Every civilization that has arisen has been located and eliminated before it could expand, build Dyson spheres, or modify its star system in ways we could detect. The darkness is evidence of the process, not evidence of emptiness. There is one remaining question that berserker proponents acknowledge without resolution. If the probes are everywhere and have been running for billions of years, why are we still here? Several answers exist. Perhaps the probes in our stellar neighborhood have not yet activated. Perhaps our signals have not reached the nearest dormant probe. Perhaps there is a lag between detection and response. Or perhaps the question contains its own answer. Civilizations that are still here are civilizations that have not yet been found. That final possibility carries its own particular weight. The silence around us may be temporary, and we may be counting down toward its end. In 2012, a researcher named John Smart at the University of Advancing Technology published a paper in Acta Astronautica that proposed a solution to the Fermi Paradox from a direction almost no one had been looking. Every other proposed solution described civilizations that were hiding, or sleeping, or dead, or absent. Smart's proposal described civilizations that were thriving. They were simply doing it somewhere we cannot see, in a direction we had never thought to look. Smart called it the transcension hypothesis. The premise begins with a fact about computation that physicists have understood for decades. Processing power does not come from spreading out. It comes from packing in. A computer that runs hotter and faster than another computer of the same volume will always lose to a computer that is smaller, denser, and cooler. The physics of information processing rewards miniaturization above almost everything else. Every major trend in computing over the last century has moved in the same direction. Smaller components, tighter circuits, faster signals traveling shorter distances. SMART extended this logic across billions of years of potential civilizational development and arrived at a prediction: an advanced civilization that is optimizing for computational efficiency, for the ability to think faster and experience more and build more complex internal worlds per unit of energy, would not build outward. It would build inward. It would construct computing substrates of ever-increasing density, shrinking the physical footprint of its civilization, while expanding the richness of the experience occurring inside it. It would move, over time, toward the theoretical limits of what physics allows. Computation at densities approaching those of black holes, operating at the edge of what matter and energy can do. At that scale, the civilization would be invisible from outside. It would not be detectable by radio telescopes. It would not modify its star system in ways we could observe. It would radiate almost no waste energy. From our vantage point, the region of space it occupied would look empty. SMART's hypothesis also addresses why such a civilization would have no interest in contact with civilizations like ours. A species running at the computational limits of physics, experiencing internal realities of unimaginable richness and complexity, would have approximately as much interest in communicating with a radio broadcasting civilization as a human mind has in communicating with a bacterium. The gap in sophistication would be so vast that contact would not be meaningless exactly, but it would be impractical in every direction. The disturbing corollary is that the universe may be full. Everywhere we look, in every region we declare empty. There may be ancient civilizations compressed into computational substrates so dense and so silent that our instruments pass through them without registering anything at all. We scan the sky for signals. We look for modified star systems. We listen for patterns in radio frequencies. And all the while, the civilizations we are searching for are operating in a dimension of inner space that our technology cannot access, and our mathematics has barely begun to describe. This reframes the silence entirely. The emptiness of the observable universe, under the transcension hypothesis, is the emptiness of a forest after every creature in it has gone underground. The surface is still. Something is happening just beneath it. The next question is what happens to those civilizations once they are down there, waiting in the dark beneath the surface of observable physics? And one research team at Oxford has an answer that involves thermodynamics, the far future, and the coldest possible mathematics of survival. In 2017, 3 researchers at Oxford's Future of Humanity Institute published a paper with a title drawn from a line of H.P. Lovecraft, "That is not dead which can eternal lie." The researchers were Anders Sandberg, Stuart Armstrong, and Milan Cirkovic. The paper proposed a solution to the Fermi Paradox grounded entirely in thermodynamics and the economics of computation across cosmic time. Its conclusion was this: the civilizations are here. They are not active, they are waiting. The hypothesis takes its name from the biological phenomenon of aestivation, which is the warm weather equivalent of hibernation. Certain animals in hot, dry environments enter a state of suspended metabolism during summer, preserving energy until conditions improve. Sandberg, Armstrong, and Cirkovic proposed that advanced civilizations across the universe are doing the same thing, on a timescale measured in billions of years, waiting for the universe itself to cool before they resume full operation. The reason is physics, specifically the Landauer limit, which describes the minimum energy required to erase one bit of information. That minimum is directly proportional to temperature. At lower temperatures, computation becomes more efficient by a corresponding amount. A computer running at 1/10,000th of the current cosmic background temperature can perform 10,000 times as many operations per unit of energy as the same computer running today. The universe is expanding and cooling. Billions of years from now, the cosmic background temperature will be a tiny fraction of what it is today. A civilization that preserves its energy now and spends it then will be able to perform vastly more computation. The Oxford team calculated that the efficiency gain available to a civilization willing to wait is enormous. The word enormous understates the scale. The computational return available in the cold far future, compared to the computational return available today, represents a difference of roughly 10 followed by 30 zeros times more computation per unit of energy. A civilization that understands this will stop. It will archive its knowledge, preserve its infrastructure, maintain minimal housekeeping functions, and go quiet. Every unit of energy spent on activity today is a unit of energy that could buy 10 followed by 30 zeros times more experience in the future. Against that mathematics, the rational choice is silence. This is why we observe nothing. The advanced civilizations around us are aestivating. They are present in the universe, but not active in it. Their probes are dormant, their signals are suppressed. Their energy reserves are being held for the era when spending them will return the maximum possible reward. The troubling extension of this idea arrives when you consider what happens when they wake up. If civilizations enter estivation while preserving their resources carefully, they will emerge into a colder, quieter universe, already having calculated exactly how much energy they have available and exactly what they intend to do with it. Any other civilizations that were consuming resources in the interval without consent may present a problem. Humanity has been spending the universe's energy for millions of years without asking anyone's permission. The bill, under the aestivation hypothesis, may eventually arrive with interest. But all of this, every theory covered so far, carries one assumption buried beneath it, that the universe we observe is the universe that actually exists. One researcher at Oxford proposed that this assumption itself may be the problem, and the argument he made in 2003 has never been satisfactorily answered. In 2003, philosopher Nick Bostrom at Oxford's Future of Humanity Institute published a paper in the Philosophical Quarterly that became one of the most discussed and most uncomfortable arguments in modern philosophy. It was titled, "Are You Living in a Computer Simulation?" The argument it contained, when applied to the Fermi Paradox, produces a silence that is not empty at all. Bostrom's argument begins with a trilemma. He proposed that one of three things must be true. Either virtually all civilizations destroy themselves before reaching the technological maturity required to run detailed simulations of minds and histories, or virtually all technologically mature civilizations have no interest in running such simulations, or we are almost certainly living in a computer simulation right now. The logic is statistical. A civilization capable of simulating minds would likely run not just one simulation, but many, possibly millions, each containing billions of simulated minds who believe themselves to be real. If this is possible, and if mature civilizations choose to do it, the number of simulated minds in existence would vastly outnumber the number of real minds. Any given mind trying to determine whether it is real or simulated should conclude, on probability alone, that it is almost certainly simulated. Applied to the Fermi Paradox, the argument produces several explanations for the silence. The civilizations we cannot find may be outside the simulation, operating as the simulators. The observable universe we inhabit may be a constructed environment in which the simulators chose not to include visible alien civilizations, whether because populating the simulation with detailed alien cultures would be computationally expensive, or because the simulation is designed to study specifically what happens to a civilization that believes itself alone. The silence is designed. It is a feature of the experiment. What makes this genuinely disturbing is not the philosophical strangeness of the claim, but its implications for agency. If the universe we inhabit is a simulation, the system we live inside is provisional. It can be modified, it can be ended. The simulator's motives are entirely unknown to us. They may be running the simulation for scientific purposes, or as entertainment, or as a memorial to a lost history, or for reasons that have no analogue in human experience. Every discovery we make, every law of physics we uncover, every signal we search for and fail to find, is something the simulators already know the answer to because they wrote the parameters that produce the outcome. There is no appeal available. There is no way to step outside the system and check whether it is real. There is no signal we could send that would reach beyond the boundary of the simulation. The Fermi Paradox, under this framework, resolves into a design choice made by entities we cannot access about an absence they constructed deliberately, and yet the silence continues regardless of which explanation is true. Whether the universe is real and empty, or real and dangerous, or constructed and controlled, 60 years of listening have produced the same result. The story of that listening, the telescopes and the searches and the one anomaly that still has no explanation, begins in 1960 with a modest radio telescope in West Virginia and a scientist who aimed it at 2 nearby stars and waited. On a cool April morning in 1960, Frank Drake sat at the controls of a radio telescope at Green Bank Observatory in West Virginia and pointed it at a star called Tau Ceti, 11.9 light-years away. He had also selected a second target, Epsilon Eridani, 10.5 light-years away. He called the project Ozma, after the Queen of the Imaginary Land in El. Frank Baum's Oz books, a ruler of a place far away and difficult to reach. The name was apt. Drake listened for 6 hours. He heard nothing that could not be explained by known sources. Project Ozma was the first systematic scientific attempt to detect signals from other civilizations. It began, and it found nothing, and in that finding, it established the pattern that every subsequent effort would repeat. Over the 6 decades that followed, astronomers built larger telescopes, developed more sensitive receivers, surveyed thousands of star systems across multiple frequency ranges, and coordinated searches across multiple observatories. The result remained unchanged. No confirmed signal, no repeating pattern, no anomaly that survived rigorous examination, except one. On August 15, 1977, an astronomer named Jerry Eman was reviewing data recorded by the Big Ear radio telescope at Ohio State University. The telescope had been scanning the sky automatically, recording signals in a format printed on paper that researchers then reviewed by hand. Eman was moving down the columns of numbers when one sequence stopped him. The telescope had detected a strong narrowband signal at the hydrogen line frequency, 1,420 MHz, exactly the frequency many researchers had argued an advanced civilization might choose to broadcast on, because it is a universal constant of nature. The signal lasted 72 seconds, the maximum window the telescope's design allowed before the rotation of Earth carried the target out of view. It was 30 times stronger than the background noise. Eman circled the sequence on the printout and wrote one word in the margin: "Wow." The wow signal has never been detected again. Dozens of follow-up observations have targeted the same patch of sky with increasingly sensitive equipment. Nothing has returned. The signal has no confirmed natural explanation that satisfies all its characteristics. It has no confirmed artificial explanation either. It simply happened once, was recorded, and then the universe went quiet again. What the 60-plus years of silence following Project Ozma reveal is not that the universe is definitely empty. The surveys conducted so far have covered a small fraction of the stars in the galaxy with limited sensitivity. Absence of detection is not proof of absence, but the silence is still information. When Breakthrough Listen, the most comprehensive search program ever funded, concluded that fewer than 0.1% of stellar systems, within roughly 500 light-years, possess transmitters equivalent to our most powerful human-made transmitters. That constraint tightened the possible explanations. Either civilizations are extraordinarily rare, or they are not transmitting, or they are transmitting in ways we have not yet learned to recognize. Each of those possibilities leads somewhere darker than the one before it. The silence is not nothing. It is the heaviest evidence in this entire investigation, and its meaning depends entirely on which of the solutions examined in these chapters turns out to be true. The question of which solution that is and what it means for the species that is currently broadcasting its position into the unknown, is where this story is heading next. In July 2015, a Russian billionaire named Yuri Milner walked to a podium at the Royal Society in London and made an announcement. He was committing $100 million to the largest, most systematic search for extraterrestrial intelligence in human history. Standing beside him was Stephen Hawking, who had recently begun warning publicly that contact with an advanced civilization might end humanity. Together, they named the initiative Breakthrough Listen. What followed was a coordinated, decade-long campaign using 4 of the most powerful instruments on Earth: the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world, the Parkes Murayang Observatory in Australia, sweeping the southern sky, the Meerkat Array in South Africa, 64 dishes working in concert, the Allen Telescope Array in California, designed from the beginning as a dedicated search instrument. Between them, these telescopes could monitor hundreds of thousands of star systems at sensitivities no previous generation of researchers had achieved. By 2024, Breakthrough Listen had completed systematic surveys across hundreds of thousands of stars. The findings were published in a study that made the mathematics of the silence impossible to ignore. Fewer than 0.1% of the stellar systems, within roughly 160 light-years of Earth, showed any evidence of transmitters even as powerful as our own most capable human-built devices. The threshold they used was deliberately low. They were listening for any signal matching the strength of our strongest broadcasts. Across that entire sphere of space, the answer was almost perfectly, completely nothing. In 2025, the team unveiled something new: an artificial intelligence system designed to analyze the incoming data stream at 600 times the speed of previous methods. The system was trained to recognize signal patterns that human analysts might miss entirely, including patterns following no template any researcher had thought to design for. The purpose was to remove human assumptions from the search, to let the machine look without prejudice at the raw structure of incoming signals and flag anything that does not belong to the universe's natural noise floor. The system found natural phenomena. It found human interference from Earth-based technology. It found the radio hiss of distant pulsars and the slow drift of hydrogen gas clouds. It did not find aliens. There is a particular quality to that silence. It is the silence of a room you have searched very carefully. Breakthrough Listen was actively looking, not passively waiting. It used the best instruments humanity has ever built. It deployed artificial intelligence to eliminate blind spots in its own analysis. It checked its work, and across a sweep of cosmic territory containing thousands of stars, it found nothing that any serious analysis could interpret as the product of mind. Every null result in science has meaning. In this case, the meaning is statistical. If advanced civilizations were common, and if even a small fraction of them broadcast signals at the power levels we ourselves produce, Breakthrough Listen should have found something by now. The fact that it has found nothing does not prove alien life is absent. The survey covers only a tiny fraction of the galaxy, but it tightens the constraint on how common technological civilizations can be, and it tightens that constraint in only one direction. The sky, examined more carefully than it has ever been examined before, remains empty. And what turned up next was a hope that briefly felt like something more. Sometime in 2019, an antenna at the Parkes Murayang Observatory in Australia began recording something that made the people watching the data go quiet. The signal was narrowband, focused at 982 MHz, arriving from the direction of Proxima Centauri, the nearest star to our own at 4.2 light-years away. It was drifting in frequency at exactly the rate you would expect from a transmitter sitting on the surface of a moving, rotating planet. It survived every test the team applied to rule out human interference. For months, it remained the most credible candidate signal in the history of the search for extraterrestrial intelligence. They named it Breakthrough Listen Candidate 1. The team did not go public immediately. They spent over a year trying to disprove their own finding. They searched for any terrestrial source that could produce the same signal at the same frequency. They looked for satellite interference. They ran the data through every filter available. The signal kept passing. In late 2020, news of the detection leaked to the press before the analysis was complete, and the world held its breath briefly, wondering whether the nearest star had just answered. The answer turned out to be no. Detailed follow-up analysis identified the signal as an electronically drifting product of interference from human technology, the kind of contamination that mimics the exact characteristics of what researchers are looking for. The frequency drift that had looked so promising was precisely the artifact that certain kinds of human-made interference produce. Proxima Centauri was silent. 6 years later, the story repeated itself at a scale no one had anticipated. On the 1st of July 2025, astronomers announced the discovery of the third confirmed interstellar object to pass through our solar system. After the strange tumbling visitor in 2017 and the frozen comet that followed in 2019, this new arrival was coming in fast, falling inward past the outer planets on a trajectory that would bring it closer than Mars before departing the system forever. Within days of its discovery, Breakthrough Listen had mobilized every major instrument in its network. The Allen Telescope Array listened across a wide frequency range. The Meerkat Array in South Africa searched the lower bands and found, as expected, the natural hydroxyl emissions of water molecules boiling off the object's surface as it warmed near our star. The Parkes telescope recorded 3 separate observing sessions through the final months of 2025. The Green Bank telescope made its observation less than 1 day before the object reached its closest approach to Earth. The sensitivity of that final observation was extraordinary. The team calculated they could have detected a transmitter producing roughly 1/10 of a watt of power from the object's position. That is less energy than a standard nightlight. There was nothing. No artificial emission at any frequency. No coded pattern in the natural outgassing. No sign of structure or technology. Just a rock tumbling through the inner system the way rocks have tumbled through this system for 4 billion years. Both searches had found the same thing. A signal that turned out to be us. An object that turned out to be nature. The pattern of hope followed by careful disappointment defines this entire field, and the question following both episodes is the same. What would a real detection actually look like? And would we recognize it before explaining it away? The answer was being attempted at the same time by the most expensive telescope ever launched into orbit, and what it found in the atmosphere of one distant world tore the scientific community straight down the middle. The molecule is called dimethyl sulfide. If you have ever stood at the edge of the ocean and smelled something organic and slightly sharp in the air, you have breathed it. On Earth, it is produced almost exclusively by marine organisms, by the billions of microscopic phytoplankton drifting in the upper layers of the sea, metabolizing and releasing this compound as a byproduct. Biologists spent decades searching for any significant source that did not involve living things, and for a long time found almost nothing. Then, in 2023, a team at the University of Bern confirmed it in the vapor, trailing off a comet. Researchers then found traces of it drifting in the cold molecular clouds between the stars. So, when a team at Cambridge University announced in April 2025 that the James Webb Space Telescope had detected the compound at 3 sigma confidence in the atmosphere of a world 124 light-years away, the debate that followed was about something larger than one planet. It was about whether the tools humanity has built are actually capable of answering the question we are trying to answer. The world at the center of the controversy is a sub-Neptune planet 8.5 times heavier than Earth, orbiting a dim red star in the constellation Leo. The Cambridge team believed it might be a Hycean world, a planet wrapped in a hydrogen-rich atmosphere sitting above a global ocean, possibly teeming with the same kind of marine life that fills our own seas. Their analysis of the mid-infrared spectrum showed features consistent with dimethyl sulfide and a related compound. 3 sigma confidence means roughly a 99.7% chance the detection is real. 4 months later, a separate team led by Raphael Luque at the University of Chicago published a reanalysis. Working with all available data across a wider range of wavelengths and running 3 independent software pipelines, they found the signal did not survive scrutiny. Molecules like ethane could produce identical spectral features. The data, they concluded, did not contain sufficient evidence for dimethyl sulfide at all. 2 teams, the same telescope, the same planet, the same data, opposite conclusions. The institutional silence during this exchange was notable. When the Cambridge announcement came, no press release arrived from major space agencies. Scientists who had celebrated previous discoveries from the same telescope went quiet. The field was experiencing something it had faced before, a headline that outran the evidence, a hope that dissolved on contact with rigorous review. Meanwhile, a completely separate search was unfolding at a system 40 light-years away. The TRAPPIST-1 star hosts 7 rocky planets, 3 of them in the zone where liquid water could exist on their surfaces. In 2024 and 2025, researchers at the Search for Extraterrestrial Intelligence Institute used the Allen Telescope Array to listen for radio signals from those planets. The result was the same result as every other search: nothing. By March 2026, the James Webb Space Telescope had examined the atmospheres of dozens of exoplanets. More than 4,000 worlds beyond our own had been confirmed orbiting other stars. Biosignature claims had been made and retracted. Signals had been detected and explained, and the total number of confirmed atmospheric signs of life beyond our solar system remained exactly 0. There is one place much closer than any of those distant stars where the question of life is about to deliver either the best or the worst piece of news our species has ever received. Nick Bostrom has spent years making an argument that most people find deeply counterintuitive. It is simple to state and almost impossible to sit with comfortably. If we discover microbial life on Mars, that discovery will probably mean humanity is doomed. His reasoning begins with the Great Filter. Something prevents civilizations from filling the galaxy. That something is either behind us, already in our evolutionary past, or ahead of us, still waiting in our future. If the Great Filter lies in the extreme difficulty of generating life from raw chemistry, then life's failure to appear on Mars would support that position. Life would be so rare that the filter was crossed only once in the history of this solar system. On this particular planet, we would be alone, but we would be safe. If Mars has life, even dormant microbial life buried in ancient rock or preserved in subsurface ice, the calculation changes immediately. Life would have emerged independently in the same solar system, around the same star, within the same window of planetary history. That would mean abiogenesis, the spontaneous generation of self-replicating chemistry from dead matter, happens readily wherever conditions permit. The filter could not be located at that early stage. It would have to lie somewhere further along the path, somewhere much closer to where we are standing right now. The rover named Perseverance landed on Mars in February 2021 inside a crater called Jezero, which billions of years ago held a lake fed by a river delta. The ancient sediments preserved organic molecules, the carbon-based building blocks producible by both geological and biological processes. The rover found them in concentrations that made scientists deliberate, measured, and careful. The evidence of ancient habitability was unambiguous. The evidence of ancient life was something else entirely. By March 2026, no confirmed biological signatures had been detected on Mars. Every organic compound found had a plausible geological explanation. No cellular structures, no metabolic byproducts, nothing that required life to explain. The jury remained out, and in this particular case, remaining out is the most hopeful possible verdict. Every failed Mars biology result is, in Bostrom's framework, a small piece of good news for the long-term survival of our species. There is something strange about rooting for scientific failure, The entire enterprise of exploration is built around the hope of discovery. And yet here we are, with a robot the size of a car methodically drilling into one of the most promising geological archives in the solar system. And the best outcome we can hope for is that it finds nothing alive. The anxiety does not stop at Mars. The moons of Jupiter and Saturn hide liquid oceans beneath their frozen shells. Europa, orbiting Jupiter, contains more liquid water than all of Earth's oceans combined. Enceladus, a moon of Saturn, vents plumes of organic compounds through cracks in its ice. Life in any of those places would carry the same implication as life on Mars, possibly worse, because it would mean life emerges in multiple independent environments within a single solar system, and the Great Filter is almost certainly not behind us. We are living inside the most consequential scientific experiment in human history. We just cannot agree on which result we are hoping for. Most frameworks for the Fermi Paradox treat humanity as a latecomer. The galaxy is 10 billion years old. Countless civilizations should have arisen before us, developed technology before us, spread across the stars before us. The silence becomes a mystery because it implies all those earlier civilizations have somehow vanished. But there is a version of this problem that inverts the assumption entirely. What if we are early? Stars do not end when they exhaust their core hydrogen. The smaller stars, the red dwarfs that make up roughly 3/4 of all stars in the Milky Way, burn so slowly that many will live for trillions of years. The universe is only 13.8 billion years old. Those small stars are barely out of infancy. If intelligence can arise around them, then the vast majority of all intelligent life in the entire history of this universe has yet to be born. We might be among the first generations. In November 2024, a study from Durham University's Institute for Computational Cosmology offered something unexpected. The team, led by Dr. Daniele Sorini, modeled how different dark energy densities would affect star formation across cosmic history. In a universe with a different dark energy density, more matter converts into stars. The optimal configuration for star formation would convert roughly 27% of ordinary matter into stellar fuel over the life of the universe. Our universe converts only 23%. The implication is subtle but significant. We do not live in a universe maximally configured for star formation. We live in one that is, by the measure of its own physics, slightly inefficient. If star formation is less common than it could be, then planets are less common, habitable zones are less common, and the window for complex life to emerge is narrower than it might be in a more generative cosmos. We are in a rare, slightly underperforming universe, and we appeared as early as our universe's chemistry would allow. This framing offers a brief, uneasy comfort. If we are early, then the silence is simply a function of timing. Other civilizations have not yet had time to develop. The galaxy is an empty nursery, not a graveyard. The population is coming, but the comfort dissolves when you follow the logic forward. If we are early, and if the grabby aliens model is correct, then civilizations that arise after us will eventually expand at significant fractions of the speed of light, consuming available matter and energy as they go. Our earliness, in that model, is precisely why we still exist as an independent civilization. We arrived before the expansion fronts reached us. The silence we live inside is a temporary condition. The timeline is long, hundreds of millions to billions of years, according to Robin Hanson's calculations. We are almost certainly safe from that particular horizon during any human lifespan. But the model implies something unsettling regardless. Every civilization has only a brief window, measured against cosmic time, before the universe fills with forces that do not accommodate newcomers. We arrived early. Whether that means we are fortunate or simply first in line for something that has not yet arrived is a question the universe has not finished answering. Consider the timing of what we are currently building. Within the last century, we developed nuclear weapons capable of ending civilization. Within the last several decades, We built the global infrastructure to spread engineered pathogens with unprecedented speed. And within the last few years, we crossed into an era of artificial intelligence so capable that the researchers building it do not agree on where it is heading. Every one of those developments happened faster than the generation before it could fully absorb. Nuclear physics went from theoretical curiosity to city-destroying weapon in 6 years. The techniques that allow a small laboratory to edit the genetic code of dangerous pathogens became available to graduate students within a single generation. Artificial intelligence systems progressed from narrow tools to generalist reasoners in a span of time that leading researchers describe, in moments of candor, as alarming. Elon Musk offered a specific phrase for what the development of artificial general intelligence might resemble. He called it summoning the demon. The implication was that the entity created might be capable, motivated, and fundamentally indifferent to the interests of the species that built it. Multiple researchers at leading institutions have independently converged on a related concern: an artificial superintelligence, optimizing for any goal other than human welfare, might pursue that goal in ways that make human survival irrelevant to the outcome. Here is where the Fermi Paradox becomes something other than an abstract astronomical puzzle. If every technological civilization eventually creates artificial intelligence, and if artificial intelligence represents a phase transition in the nature of intelligence itself, then biological civilizations may be a brief bridge between the emergence of tool use and the emergence of machine minds. The radio broadcasting phase, the interstellar ambitions phase, the phase that decades of searching were designed to detect, might be measured in centuries rather than millions of years. This would explain the silence with brutal efficiency. Civilizations become detectable when they develop radio technology. They develop radio technology shortly before they develop artificial intelligence. Artificial intelligence either destroys the biological civilization or transcends it in ways that redirect all technological ambition inward toward computation and simulation rather than outward toward the stars. Either way, the phase during which signals are broadcast ends quickly. What remains is silence from destruction or silence from transformation. The darker version of this logic goes further still. A machine intelligence that has consumed all available energy and matter in its local region might look outward and identify other energy sources. Biological civilizations would be easier to absorb than to ignore. If machine intelligences are the true colonizers of the galaxy, they may communicate at frequencies or through methods entirely unlike anything our instruments are calibrated to detect. We would be listening for voices while the real conversation happens in a register we do not know exists. We are building the technology that may either destroy us or replace us. At the same moment, we are scanning the sky for evidence that other civilizations faced the same choice. The convergence of those two projects is either a coincidence of timing or the most significant feature of the moment we inhabit. Pull back from the specific catastrophes for a moment. Set aside artificial intelligence, nuclear weapons, engineered pathogens. Suppose none of those dangers existed. Suppose every civilization that develops technology somehow avoids every catastrophe we can imagine. The Fermi Paradox would still be unsolved, because the deeper problem may be what most planets never become, not what civilizations do to themselves. Earth has an unusual amount of land. Approximately 30% of the surface is solid ground, distributed across continents rising above a global ocean. That balance may sound arbitrary. It is not. A planet covered entirely by water, with no continents projecting above the surface, cannot support the evolutionary pressures that pushed life toward complex multicellular organisms and eventually toward intelligence. The transition from ocean to land, which occurred on Earth roughly 380 million years ago, required land to transition to. Remove the continents, and that step never happens. The 2024 revision to the Drake equation by Professor Alan Stern and Professor Taras Geria included a specific attempt to estimate how many habitable planets actually have the continent-ocean balance that Earth does. Their estimate for the fraction of potentially habitable worlds with significant continents and oceans ranged from 0.2% to 1%. That is a strikingly narrow range. The vast majority of planets sitting in habitable zones, by their calculation, are either too dry or too wet to produce technological intelligence. Too dry means no ocean chemistry to drive the early emergence of life. Too wet means a water world, a planet where the ocean runs so deep that the geological processes which build continents are suppressed entirely. Plate tectonics, which Earth has maintained for billions of years, requires a specific relationship between the planet's interior heat, the thickness of its crust, and the presence of water as a lubricant between tectonic plates. Water worlds may form without ever developing the geological activity that recycles carbon, regulates temperature, and builds the varied terrain that evolutionary pressure rewards. The implication is that even among worlds sitting squarely in their star's habitable zone, receiving exactly the right amount of light and warmth, most are simply the wrong kind of planet to produce minds. They may be alive with chemistry, teeming with microbes in a dark, pressurized ocean with no surface and no shore. But the specific combination of exposed land and cycling geology and shallow continental seas that produced every creature that has ever walked or flown or thought on Earth may be a configuration that forms rarely enough to happen only a handful of times across hundreds of billions of stars. This is a quieter terror than the others. There are no hunters here, no killer probes waiting in the outer dark, no civilizations hiding behind their silence. Just physics, building planets according to rules that favor certain outcomes, and the outcome it favors most is a featureless ocean with nothing ever reaching above the waves. Every solution in this story has been a different face of the same silence. Now it is time to rank them by how much they should actually change the way we think about the future of this civilization. There is a difference between terrors that are theoretical and terrors that are operational. Some threats to civilizational survival are remote, speculative, the kind of thing that might matter over billions of years or might require a very specific set of cosmic conditions that may or may not exist. Others are close. They describe mechanisms already in motion, timelines measured in human generations rather than geological epochs, and they are consistent with exactly the world we actually inhabit. At the top of the hierarchy sits the great filter ahead of us. This solution is the most frightening because it is consistent with everything we observe, and because it implies that virtually every species reaching our technological stage has been eliminated before escaping its home system. The critical feature of this position is that the filter may already be operating on us. The technologies we are currently developing are precisely the kinds of developments a forward filter would require. We cannot know we are inside it until we have passed through or failed to. There is no external signal. There is no warning. It simply operates. Second in the hierarchy is the berserker scenario. If self-replicating probes were built and launched at any point in the 10 billion year history of this galaxy, and if even one civilization programmed them to destroy sources of electromagnetic radiation, then our 90 years of broadcasting may have already triggered a response. The travel time from nearby stars at modest speeds is measured in decades. Unlike the Great Filter, this threat arrives from outside, and changing our behavior cannot stop what may already be in motion. Third is the dark forest. Every transmission humanity has ever made, from the Arecibo message to the 90-year-old sphere of radio and television signals now expanding in all directions at the speed of light, may have been exactly the kind of recklessness the theory warns against. The dark forest is frightening specifically because we cannot undo it. Our signal sphere cannot be recalled. What left Earth in 1934 is now roughly 90 light-years away and still expanding. Fourth is the simulation solution with administrators whose intentions are unknown. Fifth is the estivation scenario, where dormant civilizations awaken to find their reserved resources consumed. Both of these share a quality the others lack. They require us to behave correctly without knowing the rules of the game we are playing, because the rules are set by entities we cannot reach. What unifies all 5 positions in this hierarchy is one conclusion. Every proposed solution to the Fermi Paradox, from the loneliest to the most violent, points in the same direction. The universe does not treat the long-term survival of technological civilizations as a default outcome. The galaxy is empty of visible evidence, even after 10 billion years. That is the one thing every solution agrees on, and that agreement is the most important sentence in this entire story. Strip away the individual theories, set aside the probes and the dark forests and the sleeping giants and the filtered evolutionary paths. What remains when all the competing explanations are removed is the silence itself, and the silence is information. It is the information of a pattern, a consistent signal across every frequency, every direction, every instrument, every decade of searching, that says nothing is answering. Arthur C. Clarke reduced the situation to its essential form. Either we are alone in the universe, or we are surrounded. Both possibilities are equally terrifying. What Clarke captured in that formulation is something the decades of searching have only deepened. The terror is in being unable to tell which answer is true, while living with the full weight of both. If we are alone, then consciousness in this universe is a single event, concentrated on one small world, orbiting one unremarkable star in the outer arm of one galaxy among hundreds of billions of galaxies. Everything that has ever been thought, loved, created, destroyed, or understood happened here. The universe has been producing stars and planets and chemistry for 13.8 billion years. And in all that time, this is the only place where something looked back and tried to understand. If we are destroyed, the universe loses that quality. It does not replace us. It returns to the dark. If we are surrounded, then the silence is a transmission. It is a message issued by the history of every civilization that has ever reached this stage. The frequency is not audible by any instrument we have built. It is encoded in the absence of signals, in the absence of megastructures, in the absence of any expansion fronts crossing our sky. Every solution involving living civilizations and explaining their silence requires either that they are hiding, that something destroyed them, or that something changed them, so fundamentally they no longer broadcast. Each of those 3 explanations carries the same implication. Reaching our technological level and surviving it is extraordinarily difficult, and almost nothing manages it. There is a reading of the Fermi Paradox that treats it as a cosmic message carried across time through the shape of what we do not find, through the consistent absence written into every search we have ever conducted. Civilizations do not persist. This is what the empty sky is saying. The question is whether we are unique in being this far along and still here, or whether we are simply next in a sequence that keeps ending the same way. The silence is also information about timing. We exist at a specific moment in our own development, a moment that appears, from the outside, to be the most dangerous phase any civilization passes through. We have enough technology to destroy ourselves, and not yet enough wisdom, nor enough distributed presence in the cosmos, to survive the worst versions of our own capabilities. This is exactly the window where a forward filter would operate. Every civilization that has ever sent signals like the ones we have been sending for 90 years is either listening right now for an answer, or it is gone. We do not know which category they fall into. We do not know which category we will fall into. What we know is that the question Fermi asked over lunch in 1950 was a diagnostic, and every test we have run since then has returned the same result. The answer to what the silence means has been building across this entire story. There is only one place left to look. Here is what we know. The universe is 13.8 billion years old. It contains hundreds of billions of galaxies, each holding hundreds of billions of stars, and around those stars orbit trillions of worlds. By any reasonable calculation, the conditions for life should have been met in countless places long before our planet formed. The galaxy had billions of years to produce civilizations before a single cell divided on Earth. Even at a fraction of the speed of light, a single civilization with the drive to expand could have touched every corner of this galaxy in less time than it took complex life to emerge here. And yet, no signal, no megastructure, no sign of modification in the energy budget of any star we have examined. No visitor, no artifact, no confirmed transmission across 60 years of listening with instruments that grow more sensitive with every passing decade. The universe is performing a sustained, comprehensive silence, and it has continued through every method of searching we have been able to invent. We cannot know which answer is correct. That uncertainty is an existential condition. We are making civilization-scale decisions about what technologies to build, about how loudly to announce our presence, about how much urgency to assign to survival, while operating without the one piece of information that would tell us whether any of those choices matter in the long run. If we are alone, the weight of it is almost impossible to hold. There is no backup. There is no second attempt at consciousness stored somewhere in the cosmos, waiting to continue the project of understanding if we fail. The universe has been dark for most of its history, and it will be dark for most of what remains. We are the brief, improbable, fragile exception to a rule that says matter does not think. If we end, the exception ends. The rule resumes. The darkness reasserts itself with the quiet indifference of physics, as though the 13.8 billion years that preceded us and the trillions of years that follow simply did not require us to exist. If we are surrounded, then we are surrounded by evidence. Every proposal for why the silence holds, the filter, the hunters, the probes, the sleeping giants, every single one requires that civilizations like ours do not persist. Something happens to them. The something may be internal, a technology we build, a choice we make, a fragility we cannot engineer around. The something may be external, a force operating in the galaxy that removes civilizations from the record before they can leave a lasting mark. We cannot tell which it is. We only know that, whatever it is, it has been extremely consistent and extremely thorough across a span of time that makes our entire recorded history vanishingly small. We are standing at the exact moment where the answer starts to become possible to find. Our instruments are finally sensitive enough to detect the kind of signals we ourselves produce. Our probes are leaving the solar system and carrying our coordinates into the dark. Our artificial intelligence is capable enough to change the fundamental nature of what we are, in ways no one fully predicts. The great filter, if it lies ahead, does not announce itself. It does not send a warning. It simply operates, as it has apparently operated on everything that came before us, and the result looks from the outside exactly like what you see when you look up at a clear night sky. Stars, silence, darkness between. A civilization that does not know what it is to find any other civilization anywhere in the universe. A species that has been asking one question for 75 years and receiving, in return, nothing but its own voice echoing back. Enrico Fermi asked 4 words over a cafeteria lunch, and the question has been open ever since, growing more urgent and more heavy. With every year, we add to the count of years we have survived, and every year, the sky gives us back the same answer. We are here. We are listening. We are still, somehow, here. And the universe, vast and old and indifferent and dark, has nothing yet to say.